In section 7.2, we're going to learn about logarithms and what they look like as a function and the value of e. So a natural base exponential function are exponential functions with base e. So you could kind of think of e as pi. It's an irrational number that's used a lot, so we just kind of have a symbol for it. And there's a button in your calculator that you can use for it. Again, the base here would be e for any natural log function. So it would be y equals a times e to the x power. E equals something around 2.71828. Again, this is an irrational number that goes on for forever, so that's why we have our own symbol and our own button for it. We'll use a natural base e for something that's like continuously compounding forever over time. So a common function that you'll see for compound interest for like a savings account, if you're putting money into an account that's earning you interest, would be a of t equals p times e r to the t power. And again, so this is kind of similar to that growth and decay model that we looked at the other day. A would be the amount in account at time t. P is your principal or your starting amount. R is your interest rate, which is usually going to be like an annual interest rate. And then T would be time, and again, we usually do this by years. So let's just look at one example here. Let's say you deposit $3,000 into a savings account that pays 5% annual interest compounded continuously. How much will you have in that account after 4 years? So I just use my function and I plug in everything where it should go. My starting amount here is $3,000, so that's what I'm going to put in for P, or my principal. I'm earning 5%, so I'm going to write in 0.05. And I want to know how much I'm going to have in my account after 4 years, so I'm going to plug in 4 for T. Finally, I'm going to plug all this into my calculator, 3,000 times e to the 0.5 times 0.05 times 4 power, or 0.2, and I get around $3,664.21. So I could see that after only 4 years, I would earn over $600. Now you might be thinking, how would I plug in e in my calculator? All you would do in a TI-84 is you would press second divide. And you'll see there's a little e right above that divide button. So that's how you use e. So next, let's talk about a logarithm. A logarithm base b of a positive number x satisfies the following definition. For b is greater than 0 and b not equal to 1, log base b of x equals y. If and only if, random math, just kind of vocab here, if and only if we could rewrite as if with 2 f's. So if you see that, just know that means if and only if. B to the y power equals x. You can read log bx as log base b of x. So that's how I would read that and say that. And log of y is the exponent to which b must be raised to get x. So basically a logarithm undoes an exponent, okay? So they're like opposites of each other. So that's kind of what we're going to focus on and work with today. So let's start by just writing something in exponential form to logarithmic form. Here we have 100 equals 10 squared. We know this, we've gone over this before. I know that those two sides are equal. I want to rewrite this, though, in logarithmic form and get rid of that exponent of 2. So I'll do it the long way first. Again, if x equals b to the y power, then log base b of x equals y. So if 100 equals 10 to the second power, then log base 10 of 100 equals 2. So basically, you take your base, you put that as the base of your log, and it's going to all that stuff is going to equal your exponent. So to go through it a little bit quicker, 81 equals 3 to the 4th power. 3 is my base, so I'm going to say log base 3 of 81 equals my exponent of 4. And we'll go over in class how to check this on the calculator. And again, can't express this enough, a logarithm basically just undoes an exponent. So that's kind of the main goal here, is to kind of work back and forth that way. So here, let's go through evaluating a logarithm. So we're going to go through doing this by hand in this video. When we're in class, we'll go through kind of a trick on how to do this as a shortcut on the calculator. But if I want to evaluate a logarithm by hand, let's say I want to find the value of log base 8 of 32. Basically what I'm doing here is I'm trying to know 8 to what power gives me 32. I'm trying to find out what exponent do I need to take 8 to give me the value of 32. So I'm going to set log base 8 of 32 equal to x. And I could rewrite that in exponential form as 8 to the x power equals 32. And what I'm going to do here is I'm going to try to rewrite some stuff around, maybe write 32 in exponential form to try to work with something there. And the easiest way to write 32 as an exponent is to do prime factorization. So we worked with this before. I'm going to take 32. I'm going to do prime factorization. When I do that, I could see that I could rewrite 32 as 2 to the 5th power. Now this is going to be helpful for me because 8 I could also rewrite with a base of 2. 8 is 2 to the 3rd power. So I could say 2 to the 3rd power to the x power equals 2 to the 5th power. Power to a power, I just multiply. So now I have 2 to the 3x power equals 2 to the 5th power. And when I have two things on either side that have the same base, I can just solve for my exponents. So 3x equals 5, x equals 5 over 3, and that would be my answer. And if I wanted to double check this, that would work out. 8 to the 5 over 3rd power does in fact give me 32. A common logarithm is a logarithm with base 10. So if you just see something like log x, you could just assume that it has a base of 10. You'll see even in your calculator, there's a log button. That just is kind of assuming that you're doing log of 10. Again, in class, we'll go over how to do log of a different base. But most logs are, again, a common logarithm is log of base 10. And also, a logarithmic function is the inverse of an exponential function, which makes sense because a logarithm, again, undoes an exponent. So just looking here, y equals 10 to the x power. We went over how kind of exponential graphs look a little bit. The key feature here, my y-intercept here would be 0, 1. If I did log of x, or log base 10 of x, that would be the inverse. I would see that one coordinate, that y-intercept is kind of inverse or flipped to be 1, 0. These are what these would look like as a graph. The last thing we're going to talk about is translating from a parent function. We're not going to get too crazy into this, but this might be a question you'd see on like an ACT or SAT. Your calculator can be really helpful for this, but we'll just talk about kind of understanding what a question like this would mean. How does the function y equals log base 4 of x minus 3 plus 4 compare to the graph of the parent function? The parent function here would be log base 4 of x. And if I'm comparing that log base 4 of x minus 3 plus 4, I'm going to think of this the same way that I looked at quadratic functions and absolute value functions. When I see that minus 3, that means I'm shifting 3 to the right. When I see that plus 4, that means I'm going 4 up. So that would be my answer. Again, the easiest way to kind of do this, or to double check this, would be to graph both of these in your calculator. So if I graph log base 4 of x and log base 4 x minus 3 plus 4, I see that. So yeah, that would kind of confirm for me that, okay, looking at that gray parent function, it looks like I shifted to the right and then up. So I'm good to go there.